time. You wake up inside it. You fall asleep inside it. It pushes you forward from the moment you were born, and it does not stop, and it does not slow down, and it does not ask your permission. It is the most obvious thing in your life. More obvious than gravity. More obvious than light. You feel it right now, this second, dragging you from the beginning of this sentence to the end. Everybody knows what time is. You know what time is. But there is a problem. The people who study time for a living have gone quiet. Not the amateurs, not the YouTube physicists. The ones at the top. The ones who write the equations and run the experiments and operate the machines. The deeper they dig into the nature of time, the less they want to talk about what they found. That silence is not modesty. It is not a gap between discoveries. It is the sound of people who reach the bottom and realize the bottom is not there. Tonight we are going where they went, and we are going to see what they saw. Let us start where any honest investigation should start, with a definition. What is time? Say it out loud if you want. Try to define it without using the word itself. You will find that your mouth opens and closes and nothing useful comes out. You are not alone. In 1687, Isaac Newton published the Principia, the book that gave us the laws of motion, the mathematics of gravity, the framework for almost everything we built in the next 300 years. Bridges, rockets, satellites. The man decoded the mechanics of the solar system with a quill and a candle. And when it came to time, he wrote this: absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external. Read that again. It sounds like a definition. It is not. It is a surrender. Flows equably. From its own nature. Of itself. Those are not explanations. Those are poetic ways of saying, I do not know why, and I am not going to look. Newton treated time the way you treat the floor in your apartment. You walk on it. You trust it. You never ask what is underneath because the question feels unnecessary. The floor is just there. Time is just there. But a man named Gottfried Wilhelm Leibniz read the Principia and asked the question Newton refused to ask. If time flows, it flows relative to what? If it moves compared to what? A river flows relative to its banks. A clock ticks relative to another clock. What does time flow relative to? Newton had no answer. His supporters had no answer. The debate between Newton and Leibniz, carried out through letters to a man named Samuel Clerk between 1715 and 1716, produced some of the most precise philosophical arguments in the history of science. And it produced zero resolution. The question was left open. Physics moved on. It accepted time as a background, a stage on which events happen, and it never explained what the stage is made of. 300 years of science built on top of a word that no one defined. But Newton was not the first to try. 2,300 years before the Principia, a man in Athens sat down and attempted the same thing. Aristotle, Book 4 of the Physics. He wrote that time is the measure of motion, clean, simple, 4 words that feel like an answer. If something moves, you can measure how long it takes to get from here to there, and that measurement is time. A rock falls, a shadow creeps across a wall, a heart beats. You count the beats, and you call the count time. For over 2,000 years, this was enough. It felt solid. It felt like a floor you could stand on. Then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that bent the floor in half. Albert Einstein, Special Theory of Relativity. Einstein showed that motion and time are not independent. They are tangled together. The speed of an object changes the rate at which time passes for that object. Move faster, and your clock slows down relative to a clock that stayed still. Time depends on motion. But motion is distance divided by time. So motion depends on time, and time depends on motion. You are standing inside a circle. Aristotle said, time is the measure of motion. Einstein proved that motion is measured by time. The definition points at the thing it is trying to define. It is like looking up a word in a dictionary and finding that the definition contains the same word. You flip to the next entry. It sends you back to the first. You flip again. Same loop. No exit. 2,300 years separate Aristotle from Einstein. Empires rose and collapsed in that gap. Continents were mapped. Atoms were split. The speed of light was measured. And the definition of time made exactly zero progress. We are still inside the loop. The floor Aristotle built and the floor Newton trusted, and the floor you are standing on right now is the same floor. And no one has ever looked underneath it. So if Newton could not define time and Aristotle's definition collapsed into a circle, what about the physicists who came after them? The ones with particle accelerators and quantum computers and telescopes that can photograph a black hole. Surely someone in the last century looked at the problem and solved it. John Archibald Wheeler. You may not know his name, but you know his work. He coined the term black hole. He was Richard Feynman's doctoral advisor. He helped design the first nuclear reactors. He co-authored the most important textbook on general relativity ever written. If anyone in the 20th century had the tools to answer the question, what is time? It was Wheeler. Here is what he said. Time is what keeps everything from happening at once. That is not a definition. That is a joke. A one-liner from a man who spent 50 years at the center of theoretical physics. He could describe the geometry of space-time. He could write equations that predict how the universe bends and stretches and collapses. And when someone asked him the simplest possible question, the one a child would ask, "What is the thing your equations are about?" he answered with a joke. Now go back 1600 years. Augustine of Hippo, a theologian in Roman North Africa. Around the year 400, he sat down to write his Confessions. And in the middle of a book about guilt and memory and God, he wrote this. What then is time? If no one asks me, I know. If I wish to explain it to one who asks, I do not know. A theologian in a toga and a physicist with a particle accelerator. 1600 years apart. Same answer, same shrug, same silence where a definition should be. This is not a gap in knowledge that science is slowly closing. This is a wall. The people who understand the universe better than anyone alive cannot tell you what time is. Not because they have not tried. Because every attempt either loops back on itself, or ends in a joke, or collapses into a confession of ignorance. The most basic element of your daily experience, the thing that separates breakfast from dinner, birth from death, this moment from the next, has no definition. Not an incomplete one. Not a rough draft. None. But maybe definitions are the wrong tool. Maybe time is like color. You cannot define red to a person who has never seen it, but you can measure the wavelength. 620 nanometers. You do not need to know what red is. You just need to count, and we are very, very good at counting time. In 1967, the General Conference on Weights and Measures made a decision. They tied the definition of a second to the cesium atom. Specifically, 1 second equals 9,192,631,770 oscillations of a cesium-133 atom transitioning between two energy levels. That number is not round because nature is not round. It is precise because the atom is precise. Every cesium atom in the universe vibrates at exactly the same frequency. It does not drift. It does not age. It does not care whether it is sitting in a lab in Colorado or flying through space at half the speed of light. The count is always the same. By the 2010s, the clocks got better. Optical clocks using strontium atoms reached a precision of 1 part in 10 to the 18th. That is 18 zeros after the decimal point. A clock like that could run for the entire age of the universe, 13.8 billion years, and lose less than a single second. These clocks are so sensitive that if you lift one by a centimeter, just 1 centimeter, it measures a different rate of time. Gravity changes by a fraction at that height, and the clock sees it. We built machines that can detect time bending across the width of your hand. Now ask yourself a question. What are these machines counting? They are counting oscillations, vibrations of an atom, transitions between energy states. They are not counting time. They are counting a process and calling the count time. The word second is a label we attach to a number of atomic vibrations. The vibrations are real. The label is ours. We have measured time more precisely than any other quantity in the history of science. And we have no idea what we are measuring. The instrument is perfect. The understanding is missing. We built a ruler that can measure a billionth of a second, and we cannot tell you what a second is. But here is where you grab the next handhold. You say, fine, nobody can define time. The clocks count vibrations and call it time, and maybe that is just a label. But time does something that is obvious and undeniable. It moves forward. Coffee cools, eggs break, you get older. Yesterday is gone and tomorrow is coming. And there is a direction to all of this that you can feel in your bones. The arrow of time. It is the most reliable thing in your experience. Whatever time is, it points somewhere. Except it does not. Not in the equations. In 1954, a German physicist named Gerhard Luders proved a theorem. A year later, Wolfgang Pauli extended it. The result is called the CPT theorem. It states that the fundamental laws of physics are symmetric under the reversal of three things: charge, parity, and time. Flip all three, and nothing breaks. The equations of electromagnetism written by Maxwell in the 1860s. Symmetric. Run them backward, every solution still works. The Schrödinger equation, the backbone of quantum mechanics. Symmetric. Reverse the direction of time and every process plays out just as cleanly in reverse. Einstein's general relativity. Symmetric. A planet orbiting a star looks exactly the same whether you play the film forward or backward. Every fundamental law of physics that we have ever discovered works in both directions of time. Forward and backward are identical in the mathematics. The arrow you feel, the one that turns eggs into omelettes and never turns omelettes into eggs, is nowhere in the code. Think about what that means. You live your entire life moving in one direction. Every cell in your body ages in one direction. Every memory you have points in one direction. And the laws that govern the atoms inside those cells and the electrical signals inside those memories do not have a direction. They do not know the difference between forward and backward. You do. They do not. The question is obvious. If the laws are blind to direction, where does the arrow come from? In 1872, a physicist named Ludwig Boltzmann found the source. Entropy. The word means disorder, but that is a shortcut. What it really means is probability. Think of your kitchen counter. You set down a glass of water. The glass is intact. The water is inside. That is an ordered state. There is exactly one way for the glass to be sitting there, whole, with the water inside. Now push it off the edge. It shatters. Water everywhere. Shards on the floor. That is a disordered state. And there are billions of ways for it to look like that. Billions of arrangements of glass and water that all qualify as a mess. Boltzmann's insight was simple and brutal. The universe does not prefer disorder. It does not choose chaos. It just has more room for it. There are overwhelmingly more ways to be messy than to be neat. So if anything changes at all, it will almost certainly change toward the mess. That is the arrow. That is the direction. Coffee cools because there are more ways for heat to spread out than to stay concentrated. Smoke fills a room because there are more ways for molecules to be scattered than clumped. You get older because there are more states of you that are broken than states that are whole. Boltzmann wrote this into mathematics. The H theorem. A proof that entropy increases over time. For the first time in history, the arrow had a mechanism. But Boltzmann was not a man who stopped at the surface. He followed his own equation deeper, the way you follow a crack in a wall to see where it leads. And what he found at the end of the crack was not a foundation. It was a hole. If entropy explains the arrow, then the arrow is a consequence, not a law. A consequence of what? Of the starting point. The universe had to begin in a state of very low entropy, extreme order, everything packed tight and arranged just so. Then, it began to fall apart, and that falling apart is what you experience as the passage of time. But why was the starting point ordered? What arranged it? What law demanded that the universe begin clean instead of messy? Boltzmann looked for the answer for 30 years. He built the field of statistical mechanics. He gave physics tools it still uses today. And he never found the reason. Every road led back to the same hole. The starting condition is assumed, not derived, not explained. Assumed. In 1906, in a hotel room in Duino on the coast of Italy, the search ended. Boltzmann did not survive his own discovery. The man who gave the arrow its equation could not find the ground the equation stands on, and that ground is still missing. For nearly 100 years after Boltzmann, the hole just sat there. Physicists walked around it. They used his equations. They taught his entropy. They built careers on the arrow he described. But they did not look down. Then, in the year 2000, a philosopher of physics named David Albert looked down. He published a book called Time and Chance, and in it, he gave the hole a name, the past hypothesis. Here is what it says. The second law of thermodynamics, the law that entropy increases, the law that gives time its arrow, only works if you add one extra assumption. The universe began in a state of extremely low entropy. That is the past hypothesis. It is not a conclusion. It is not a derivation. It is an axiom. A rule you must accept before the rest of the machinery starts running. Without it, the arrow has no starting point. Without it, entropy has no direction to increase from. Without it, your coffee has no reason to cool. Now ask yourself how likely that starting state is. Roger Penrose, one of the most respected mathematical physicists alive, calculated the probability. He asked a simple question. Out of all possible ways the universe could have begun, how many of them have entropy low enough to produce the arrow we observe? His answer is a number, but it is not a number you can hold in your head. It is 1 in 10 to the power of 10 to the power of 123. Write that down. 10. Raise it to the 123rd power. That gives you a number with 123 zeros. Now raise 10 to that. The result has more digits than there are particles in the observable universe. You could not write it on a piece of paper if the paper were the size of the cosmos. That is the probability of the starting condition that makes your coffee cool, and your memories point backward, and your body age in one direction. The entire arrow of time rests on a coincidence so unlikely that the number describing its improbability does not fit inside the universe the coincidence created. And no one knows why it happened. No law explains it. No equation predicts it. You just have to accept it. The floor beneath the arrow is not thin. It is not cracked. It is not there. But maybe the floor is not missing. Maybe it was never supposed to be there. Maybe the question itself is wrong. In 2004, a physicist at Caltech named Sean Carroll and a researcher named Jennifer Chen published a paper that turned Boltzmann's problem on its head. They proposed that the universe did not begin in a state of low entropy. It began in the opposite. Maximum entropy. Total equilibrium. No structure, no gradient. No arrow. A state where nothing happens because there is no difference between here and there, between hot and cold, between anything and anything else. That does not sound like a beginning. It sounds like an ending, and that is exactly the point. In Carroll and Chen's model, the universe starts at the bottom, not the top. And from the bottom, random fluctuations create pockets of lower entropy, not one pocket, two, growing in opposite directions. Think of a puddle of water on a flat table. The water sits still. That is equilibrium. Now tilt the table slightly. The water flows to one side. But if you could tilt the table in two directions at once, the water would flow both ways. Two streams, two directions, two arrows. Carroll and Chen's model says the universe does exactly that. From the equilibrium point, two branches emerge. In one branch, entropy increases in what we would call the forward direction. That is our universe, our arrow, our future. In the other branch, entropy increases in the opposite direction. If you lived there, your arrow would point the other way. Your past would be our future. Your memories would form in the direction we call backward. And you would feel exactly as normal as you feel right now. Neither branch is the real one. Neither arrow is the true direction. Both are local. Both are accidents of position. You experience time moving forward not because the universe has a direction, but because you happen to be standing in one arm of a structure that has two. The arrow of time is not a law carved into reality. It is the view from where you are standing. Somewhere on the other side of a point that has no before and no after, time points away from you. And the people there, if there are people there, are just as convinced that their direction is the only one. So the arrow is not a law. It is a local accident. The direction you call forward might be someone else's backward. But there is one thing left that feels absolutely solid. Right now, this moment. You are reading these words and you are here in the present. And whatever time is, whatever direction it points, the present moment is real. It is the one thing you cannot argue with. You are in it, except you are not. In 1905, a 26-year-old clerk in a Swiss patent office published a paper that dismantled the idea of now. Albert Einstein, Special Theory of Relativity. The paper is famous for E = mc squared, but that is not the part that matters here. The part that matters is what Einstein proved about simultaneity. Two events that happen at the same time for you do not happen at the same time for someone moving relative to you. This is not a trick of perception. This is not about clocks running slow or signals arriving late. This is the structure of the universe itself. Imagine two lightning bolts strike at the same moment. One hits a tree to your left, one hits a tree to your right. You see them at the same instant. They are simultaneous. Now imagine a person on a train moving past you at high speed. That person sees the same two bolts, but because the train is moving toward one bolt and away from the other, the light from each bolt reaches the train at different times. For the person on the train, the bolts did not happen at the same moment. One happened first, the other happened second. And here is the part that breaks things. Neither of you is wrong. There is no experiment you can do to prove that your version is the real one. There is no referee. There is no universal clock somewhere in the sky that records the true order of events. Your now is yours. The passenger's now is different. Both are equally real, both are equally valid. And there is no physical law that picks one over the other. The present moment is not a feature of the universe. It is a feature of your velocity. Change your speed, and you change your now. The thing you thought was the most solid ground you could stand on, this instant, right here, turns out to depend on how fast you are moving through space. Stand still, and you have one present. Move, and you have another. Neither is more real than the other. The universe does not have a now. You do. If there is no universal now, then what does the universe look like to someone who can see all of it at once? Not from inside, not from one speed, not from one position, but from above. The whole thing. Past, present, future, everything. In 1908, 3 years after Einstein's paper, a mathematician named Hermann Minkowski stood in front of an audience in Cologne and gave a lecture that changed the shape of reality. Minkowski had been Einstein's teacher. He understood the mathematics of special relativity better than almost anyone alive. And he realized something that Einstein himself had not yet fully seen. Space and time are not separate things. They are one thing. A single four-dimensional structure. A block. Minkowski said it plainly. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Think about what a block means. A city exists all at once. The north side does not stop existing because you are standing on the south side. The streets you visited yesterday are still there. The streets you will visit tomorrow are already there. You do not think the city is being created in front of you as you walk and destroyed behind you as you leave. The city just is. All of it. At once. Minkowski's block universe says the same thing about time. Your birth is in the block. Your death is in the block. The moment you are experiencing right now is in the block. And so is every moment before it and every moment after it. They are all equally real. None of them is more present than any other. The sensation that you are moving through time, that the past is gone and the future has not arrived, that sensation is not a property of the block. It is a property of you. You are a line drawn through a four-dimensional object, and you experience that line one point at a time because that is what it is like to be inside the block. But the block does not move. The block does not flow. The block does not tick. It just sits there. Complete. Finished. Every moment you will ever live already exists in the same way that every page of a closed book already exists. You are not writing the story. You are reading it. And the book was finished before you opened it. That sounds like philosophy. A mathematical construct. Lines on a blackboard. You could listen to everything Minkowski said and walk away thinking it is a beautiful idea that has nothing to do with the physical world. But in 1971, two physicists named Joseph Hafele and Richard Keating decided to stop arguing about it and measure it. Their experiment was simple. They took 4 cesium atomic clocks, the most precise timekeeping devices available, and they put them on commercial airline flights, regular passenger jets, the kind you book a seat on and eat peanuts and watch a movie. 2 flights went eastward, around the world with the rotation of the Earth. 2 went westward, against the rotation. A 5th set of clocks stayed on the ground at the United States Naval Observatory in Washington. The flights lasted days. The clocks flew in the overhead compartments like carry-on luggage. When the planes landed, Haffel and Keating compared the numbers. The clocks that flew east had lost 59 nanoseconds compared to the ground clocks. The clocks that flew west had gained 273 nanoseconds. Not roughly, not approximately. The numbers matched the predictions of both special and general relativity to within the margin of error. The clocks that traveled came back showing a different time than the clocks that stayed. Not because they malfunctioned, not because of turbulence or temperature or cabin pressure, because time itself passed at a different rate for objects moving at a different speed and sitting at a different altitude. Those clocks left Washington and came back from a slightly different version of the present. A few hundred nanoseconds away from the now that existed on the ground. You can hold one of those clocks in your hands. You can read the number. It is not a theory. It is not a thought experiment. It is a machine that went on a commercial flight and came back with proof that your now is not the same as everyone else's now. The difference is tiny at airplane speeds, billionths of a second. You would never feel it. But the difference is not zero. And if it is not zero at 900 kilometers per hour, imagine what it is at 90% of the speed of light. The gap stops being invisible. It becomes years, decades. The present moment is not universal, it is personal. It depends on where you are and how fast you are going. And the instruments confirmed it in the overhead bin of a passenger jet. Every day, 24 satellites orbit the Earth at an altitude of 20,200 kilometers. They move at 3.9 kilometers per second. Each one carries an atomic clock, and each one of those clocks ticks at a different rate than the clock on your wrist. 2 effects at once: gravity and speed. General relativity says that a clock in weaker gravity runs faster. The satellites are higher up, farther from the center of the Earth, so gravity is weaker there. Their clocks gain 45 microseconds per day compared to clocks on the ground. Special relativity says that a clock moving faster runs slower. The satellites are moving at nearly 4 kilometers per second, so their clocks lose 7 microseconds per day. Add them up. Plus 45. Minus 7. The net difference is 38 microseconds every single day. That does not sound like much. 38 millionths of a second. You would not notice it if you tried. But the system that depends on those clocks is the Global Positioning System. GPS. Your phone uses it every time you open a map. The way it works is simple. Your phone receives a signal from at least 4 satellites. Each signal carries a timestamp. Your phone compares the timestamps and calculates how far away each satellite is. From those distances, it figures out where you are standing. The math depends entirely on the timestamps being accurate. If the clocks on the satellites drift by 38 microseconds, and no one corrects them, the position calculation drifts with them. After 1 day, the error is 10 kilometers. After 2 days, 20. Within a week, your phone would tell you that you are in a different city. So the engineers correct it. Every satellite adjusts its clock to account for the fact that time on orbit does not pass at the same rate as time on the surface. Every timestamp is modified. Every position you have ever seen on a map is the result of someone compensating for the difference between your now and the satellite's now. 2 billion people use this system every day. 2 billion people open an app and trust it to tell them where they are. And the only reason it works is that the engineers built the difference between 2 versions of the present into the code. Your phone knows something about time that most people refuse to consider. Now is not the same everywhere. It depends on where you are. It depends on how strong gravity is. And the machine in your pocket has been quietly correcting for that every second of every day since you started carrying it. So physics has taken the outside apart. Time has no definition. Its direction is an accident. The present moment depends on your speed and your altitude. But there is still one place where time feels absolutely real. Inside your head. Close your eyes. You can feel it right now. A flow. A current. The sensation that this moment is happening, and then it is gone, and the next one arrives. Whatever the equations say, whatever the satellites measure, you experience time passing. That experience is not a theory. It is the most immediate thing you have. But in 1983, a neuroscientist named Benjamin Libet designed an experiment that cracked the inside open the same way Einstein cracked the outside. The setup was simple. A person sits in a chair. In front of them is a clock with a single dot moving around the face. The person is told to flex their wrist whenever they feel like it. No schedule, no signal. Just move when you decide to move. 3 things are measured. First, the electrical signal in the motor cortex of the brain. Electrodes on the scalp detect when the brain starts preparing the movement. Second, the moment the person reports deciding to move. They watch the dot on the clock and remember where it was when they felt the urge. Third, the actual movement of the wrist. The order should be obvious. You decide, then your brain fires, then your wrist moves. Decision first, signal second, action third. That is what it feels like from inside. That is the order your experience reports. Libet measured a different order. The electrical signal in the motor cortex appeared 350 milliseconds before the person reported deciding. The brain was already preparing the movement before the conscious mind knew it was going to happen. Your brain starts the action. Then it tells you that you chose it. The sequence you experience, the one where you decide and then your body moves, is not what happened. It is a reconstruction. Your brain made the decision, then built the feeling of having made it, and delivered both to your consciousness packaged in the wrong order. You are not making choices in the present. You are being informed of choices that have already been made, and the notification arrives with a timestamp that your brain moved backward to make the story feel right. Libet showed that the order is faked, but maybe that is a narrow case, one specific situation, a wrist flexing, a single decision. Surely the rest of your experience of time is more reliable. Surely the simple sensation of now, the feeling that this second is happening in real time, that part is accurate. In the early 2000s, a neuroscientist named David Eagleman at Baylor College of Medicine started pulling that thread. What he found is that the now you experience is not a moment, it is an edit. Your brain does not receive the world in one piece, it receives it in fragments. Light hits your eyes, sound hits your ears, pressure hits your skin. Each signal travels to the brain at a different speed through a different pathway. Vision is slow, sound is faster. Touch depends on where on your body it happens. A tap on your nose arrives at the brain faster than a tap on your toe, because the distance is shorter. The differences are not trivial. They range from 80 to 500 milliseconds depending on the sense and the location. Half a second. That is the gap between the fastest signal and the slowest. But you do not experience a gap. You do not hear the glass shatter and then see it break a half second later. You experience both at the same time in one seamless now. Because your brain waits. It collects the fragments. It holds the fast ones back until the slow ones arrive. Then it stitches everything together into a single moment and presents it to you as the present. You are never experiencing what is happening now. You are experiencing what happened a fraction of a second ago, reassembled and smoothed out and delivered to your awareness as if it were live. There is a name for the glitch where this system shows its seams. Chronostasis. You look at a clock. The second hand seems to freeze for a moment that is just slightly too long. Then it starts ticking normally. What happened is that your brain moved your eyes to the clock, and during the movement it had no stable image. So it took the first frame it received after the eyes stopped moving, the image of the second hand in one position, and stretched it backward in time to fill the gap. It pasted the new image over the blank spot. You are not watching time. You are watching a reconstruction of time that your brain assembled from pieces and stitched together with thread that is not there. In 2002, a neuroscientist named Patrick Haggard at University College London tested exactly that. The experiment was clean. A person presses a button. 250 milliseconds later, a tone plays. Simple cause and effect. Button first, sound second. The person knows they pressed the button. The person knows the tone followed. All Haggard asked them to do was report when each event happened. When did you press the button? When did you hear the tone? The answers were wrong. Not randomly wrong. Systematically wrong. Every subject reported pressing the button slightly later than they actually pressed it. And every subject reported hearing the tone slightly earlier than it actually played. The brain moved the two events toward each other. It shrank the gap. It took the cause and the effect and slid them together in time as if it wanted them to be closer. As if it needed the connection to feel tight and immediate. Haggard called this temporal binding. Your brain does not passively observe the relationship between what you do and what happens next. It edits the relationship. It decides that these two events are connected, and then it adjusts the timestamps to make the connection feel stronger. You press a light switch. The light comes on. You feel like it happened instantly. It did not. There was a gap. Your brain closed the gap because a tight link between action and result is more useful than an accurate one. Now, scale that up. Every time you feel that one thing caused another, every time you experience the flow from cause to effect, you're not detecting a relationship in the world. You're watching your brain construct a relationship and paste it over the raw data. The cause did not lead to the effect in the way you felt it. Your brain decided they were linked and then recut the timeline to make the link feel real. Causality as you experience it is not a discovery. It is a production. Your brain is not a camera recording what happens. It is an editing room that decides what the story is and then cuts the footage to match. So the order is faked. The duration is faked. The feeling of cause and effect is faked. 3 layers of your experience of time, and all 3 turn out to be constructions. But maybe the machinery underneath is still connected to something real. Your brain has a clock, not a metaphor, an actual oscillation. Neurons fire in rhythmic patterns. The one that matters most for the experience of time is called the gamma rhythm. It cycles between 30 and 100 times per second. 30 Hz at the low end, 100 Hz at the high end. That rhythm is the refresh rate of your conscious experience. It is the rate at which your brain samples the world, assembles a frame, and presents it to you as now. If the gamma rhythm were stable, you could argue that at least the raw machinery of time perception is anchored to something fixed. A biological metronome. Steady. Reliable. But it is not steady. In 2016, a team led by Enzo Tagliazucchi published a study on what happens to the gamma rhythm under certain substances that alter brain chemistry. The rhythm breaks apart. The synchronized firing patterns that normally hold your experience of time together become scattered. Some regions speed up, others slow down. The unified frame dissolves. And the subjective experience of time changes with it. Seconds stretch into what feels like minutes. Minutes collapse. The present moment becomes thick, elastic, unfamiliar. Meditation does something similar. A study by Mark Whitman in 2015 showed that experienced practitioners of Vipassana meditation have measurably different gamma patterns. Their subjective experience of duration shifts. Time feels slower or faster, or both at once depending on the depth of the practice. Trauma does it. A car accident. A fall. People report that time slowed down, that they saw everything in detail, that a 3-second event felt like 30. Adrenaline floods the brain, and the sampling rate spikes, and suddenly there are more frames per second, and each second feels longer. Your experience of time is not wired to the universe, it is wired to a frequency generated by tissue inside your skull. Change the frequency and time changes with it. Speed it up and the world slows down. Slow it down and the world speeds up. The sensation of seconds passing, the feeling that gives you more certainty than anything else in your life, is generated by an electrical oscillation that can be bent by chemistry, by practice, by a sharp enough spike of fear. Two independent directions have now reached the same conclusion. Physics looked at time from the outside and found that it is not fundamental. Neuroscience looked at time from the inside and found that it is constructed. The outside and the inside agree. The question is whether there is a level deeper than both. A level beneath physics and beneath the brain. The quantum level. The bottom of the bottom. If time is real anywhere, it should be there. In 1978, John Archibald Wheeler, the same man who answered the question, "What is time?" with a joke, proposed an experiment. Not a real one. A thought experiment. He called it delayed choice. The setup uses the most basic piece of equipment in quantum mechanics, a beam splitter. You fire a single photon at it. The beam splitter gives the photon two possible paths, left or right. If you put detectors at the end of each path, you find out which way the photon went. It went left or it went right. Particle behavior. One path. One answer. But if instead of the detectors you put mirrors that redirect both paths so they meet again, and you place a second beam splitter at the meeting point, something changes. The photon interferes with itself. It produces a pattern that is only possible if the photon traveled both paths at the same time. Wave behavior. Two paths. No definite answer. This is standard quantum mechanics. The strange part is what Wheeler added. He said, what if you make the decision after the photon has already entered the apparatus? The photon hits the first beam splitter. It starts traveling. And while it is in transit, you decide whether to insert the second beam splitter or not. If you insert it, the photon behaves like a wave, both paths. If you do not, it behaves like a particle, one path. The photon's behavior in the past depends on a decision you have not yet made. Wheeler proposed this in 1978 as a thought experiment. In 2007, A team led by Vincent Jacques at the École Normale Supérieure in Paris built it. Single photons, real beam splitters, real detectors. The decision to insert or remove the second beam splitter was made by a random number generator after the photon had already passed the first one. The results matched Wheeler's prediction exactly. When the second splitter was inserted, the photon had travelled both paths. When it was removed, the photon had travelled one. The decision made after the photon entered the apparatus determined what the photon had done before the decision was made. Not influenced, determined. This has been reproduced dozens of times in laboratories around the world. No hidden variable model has survived the tests. The photon did not know in advance what you were going to decide. It did not hedge its bets. The event in the past was not settled until the measurement in the future occurred. On the deepest level of physical reality, the level beneath atoms, beneath molecules, beneath everything you can see and touch, the order of before and after is not fixed. The future reaches back and shapes the past, and the equipment that proved it fits on a laboratory table. In 1964, a physicist at CERN named John Bell sat down and wrote a theorem that most people have never heard of and that changed everything. Bell's theorem. It asks a simple question. Can the strange behavior of quantum particles be explained by some hidden mechanism we have not found yet? Some deeper layer of reality where things make sense and causes come before effects and information travels at a normal speed? Bell proved mathematically that the answer is no. There is no hidden layer. The strangeness is not a gap in our knowledge. It is the way things are. In 1982, a French physicist named Alain Aspect tested this. He took two photons, entangled them, and sent them in opposite directions. Then, he measured a property of each photon. The results were correlated, not loosely, perfectly. When one photon was measured and found spinning one way, the other photon, no matter how far away, was always found spinning the opposite way. Always. Every single time. That by itself is not shocking. You could imagine that the photons agreed on the answer before they separated, like two coins flipped from the same hand. But Bell's theorem rules that out. The correlations are stronger than any pre-arranged agreement could produce. The only way to get the numbers aspect measured is if the two photons are connected in a way that does not involve a signal traveling between them. No signal, no light beam, no force, no wave, nothing crosses the space between them. The correlation simply exists, instantaneously, across any distance. Einstein saw this coming. He called it spooky action at a distance. He spent the last decades of his life arguing that it proved quantum mechanics was incomplete, that there must be a hidden variable, a deeper mechanism, something that restores sanity. Bell proved there is no hidden variable. Aspect confirmed it in the lab. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for experiments that settled the question permanently. The correlations are real. They do not travel through space. They do not travel through time. They exist outside both. Two particles separated by a galaxy respond to each other without a moment passing between the response. Not faster than light. That would still be inside time. This is outside time. The connection does not use time at all. Einstein called it an error. The error was Einstein's. If entanglement does not need time to exist, then the question flips. Maybe time needs entanglement. In 2013, two physicists published a conjecture that sounds like it was pulled from the wrong side of a mirror. Juan Maldetina, one of the most cited theoretical physicists alive. Leonard Susskind, one of the founders of string theory. The conjecture is called ER equals EPR. Two sets of initials, two papers from 1935, both by Einstein, though with different co-authors. ER stands for Einstein-Rosen. Their paper described bridges in space-time, tunnels connecting two distant points. You know them as wormholes. EPR stands for Einstein-Podolsky-Rosen. Their paper described entanglement, two particles connected across distance without a signal between them. For 78 years, these were considered completely separate phenomena. Wormholes were geometry, entanglement was quantum mechanics, different fields, different mathematics, different buildings on the university campus. Maldacena and Susskind proposed that they are the same thing. Every pair of entangled particles is connected by a wormhole. Every wormhole is a manifestation of entanglement. The bridge and the connection are one object seen from two different angles. Now follow that logic. If entanglement and space-time geometry are the same thing, then space-time is not the container that holds quantum connections. Space-time is built from quantum connections. The fabric of reality is not a stage on which entangled particles perform. The fabric is the performance. Take away the entanglement and the stage disappears. There is no space, there is no time, there is only a web of correlations, and when you zoom out far enough, when enough correlations accumulate, they start to look like distance and duration and cause and effect. Time does not produce entanglement. Entanglement produces time. The thing you thought was the foundation turns out to be the product. The thing you thought was the product turns out to be the foundation. And the two physicists who proposed this are not fringe figures writing papers in a basement. They are at the center of theoretical physics, and no one has proven them wrong. If time is built from entanglement, then there should be a mechanism, a way to show precisely how the experience of time emerges from a system that does not contain it. In 1983, two physicists named Don Page and William Wouters proposed exactly that. The idea is so clean it almost feels like a trick. The universe is a closed system. Nothing exists outside it. There is no clock on the wall of the cosmos ticking away the seconds from some external shelf. In quantum mechanics, a closed system that contains everything is described by a single state, one total state. And that state does not change. It cannot change, because change means something is different from one moment to the next, and moments require a reference outside the system, and there is no outside. The universe as a whole is static, not frozen in time. The word frozen does not apply. There is no time for it to be frozen in. Now do one thing. Split the system into two parts. Call one part the clock. Call the other part everything else. Let the clock observe everything else. The quantum correlations between the two parts, the way their states are tangled together, begin to look like evolution. The clock sees the rest of the universe changing. It registers a before. It registers an after. It measures a gap between them. From inside, there is time. From outside, there is none. In 2013, a team led by Ekaterina Moreva at the National Institute of Meteorological Research in Turin built this with photons. Two entangled photons in a laboratory. An observer outside the entangled pair measured the system. No change, no sequence, no duration, nothing happened. An observer entangled with one of the photons measured the other. Change, sequence, duration, time, same photons, same lab, same apparatus. Two realities depending on where you stand. You have never stood outside. You cannot. You are tangled into everything around you. You are a part of the universe looking at another part, and the thing you see between yourself and the world, that gap you call a second, that flow you call the present, is not the universe moving. It is what it looks like when a fragment tries to measure the whole from inside and mistakes the measurement for a river. In 1967, a physicist named Wheeler-DeWitt wrote down an equation. It was not a long equation. It fit on a single line. But what it described was everything. The entire universe. All of it. Every particle, every field, every force, every galaxy, every photon, every atom in your body, everything that exists, wrapped into one quantum mechanical expression. DeWitt was completing an idea that John Wheeler had been circling for years. The question was simple. We have quantum mechanics, which describes small things. We have general relativity, which describes big things. What happens when you write a quantum equation for the biggest thing there is? The universe itself? The answer is the Wheeler-DeWitt equation. And the answer has a problem. There is no t. The variable for time does not appear. Not because DeWitt forgot it, not because he simplified the math, not because he chose a convenient shorthand. When you write quantum mechanics for a closed system that contains everything, the mathematics does not produce a time variable. It is not hiding somewhere in the equation waiting to be extracted. It is not buried inside another term. It is absent. The equation describes a universe in which nothing happens. Not a universe where things happen slowly. Not a universe where time is hard to detect. A universe where the concept of happening does not apply. Everything simply is, all at once, always. This is called the problem of time in quantum gravity. It has been open since 1967. It is not a footnote. It is not a minor technical issue that theorists argue about at conferences, and then forget. It is the central obstacle to unifying the two greatest theories in physics. General relativity needs time. It is built on time. Time bends, time stretches, time tells matter how to move. Quantum mechanics, when applied to the whole universe, erases time. It produces a description in which the word when has no meaning. Two frameworks, both confirmed to extraordinary precision. One requires time to exist, the other says it does not. And for 57 years, no one has figured out how to reconcile them. But someone took the absence seriously. In 2004, a physicist named Carlo Rovelli published an essay with a title that most of his colleagues probably wished he had not chosen. Forget Time. 2 words. An instruction. Rovelli is not a philosopher writing from the margins. He is one of the founders of loop quantum gravity, one of the leading candidates for a theory that unifies general relativity and quantum mechanics. He has spent his career working at the deepest level of physical reality. And his conclusion after decades of work is that time is not a feature of that level. Here is his argument. When you have complete information about a system, when you know the exact state of every particle and every field, you do not need time. You can describe the system as a set of relationships between variables. This variable is correlated with that variable. This state is connected to that state. No before, no after. Just a web of relations. Time only appears when you do not have complete information. When you are missing details about the microscopic state of the system, you are forced to describe it statistically. And in the statistical description, a parameter shows up that behaves like time. It increases. It gives you a direction. It lets you talk about change and sequence and duration. But it is not fundamental. It is a consequence of your ignorance. Rovelli published this in a book in 2017 called The Order of Time. It was translated into more than 40 languages. It sold millions of copies. The argument is not hidden. It is sitting on bookstore shelves around the world. Time is what appears when you do not know enough. It is the blur you see when your vision is not sharp enough to see the individual threads. Sharpen the vision and the blur disappears. Gain complete knowledge and time disappears with it. It is not that we cannot find time at the fundamental level. It is that time is the name we give to not being able to see the fundamental level. The thing you feel every second of your life is not a feature of reality. It is a feature of the limits of your perspective. Remove the limits, and you remove the time. Rovelli removed time, but he left something behind. Change. Relations between variables still shift. Correlations still exist. The web still has a structure even without a clock ticking above it. A physicist named Julian Barbour looked at what Rovelli left behind and removed that too. In 1999, Barbour published a book called The End of Time. The title is not a metaphor. He means it literally. Barbour's proposal is that the universe is not a sequence of events. It is a collection of configurations. Each configuration is a complete arrangement of every particle in the universe. A snapshot. A single frozen frame that contains everything. The position of every atom. The state of every field. The shape of every galaxy. In Barbour's model, these configurations do not follow one another. There is no first frame and second frame and third frame. There is no order. There is no progression. There is just a vast space of all possible configurations, and Barber calls this space Platonia. Every possible arrangement of the universe exists in Platonia. The one where you are reading this. The one where you stopped reading 5 minutes ago. The one where you were never born. They are all there. None is more real than any other. None comes before or after any other. Now here is the part that makes it hard to breathe. Some of these configurations contain structures that look like records of the past. A brain with memories. A fossil in a rock. A photograph on a shelf. Light from a distant star that has been traveling for 1 million years. These structures exist inside the configuration. They are part of the snapshot. And your brain, which is also inside the snapshot, looks at these structures and concludes that there must have been a past. There must have been a sequence. There must have been a film reel leading up to this frame. But there is no film reel. There is no projector. There are only photographs. And on some of those photographs, there are images of projectors. Your memories are not recordings of events that happened. They are features of the configuration you exist in. The sensation that time passed, that yesterday happened, that you were once a child, is not a report from the past. It is a pattern inside a frozen frame. Barber is not saying that the past is gone. He is saying the past was never there. There was no sequence to begin with. There is only now. And now is not a moment in time. It is a configuration that contains the illusion of time within its structure. Someone does. Loudly. In 2013, a physicist named Lee Smolin published a book called Time Reborn. The title is a direct answer to Barber. Barber said time is dead. Smolin says time is the only thing that was ever alive. Smolin is not a minor voice. He co-founded the Perimeter Institute for Theoretical Physics, one of the most important research centers in the world. He has spent decades working on quantum gravity, and his conclusion is the exact opposite of Ravelli's and Barber's. Time is not an illusion. Time is not a side effect of ignorance. Time is not a pattern inside a frozen photograph. Time is real, more than real. It is the only thing that is real. Here is Smolin's argument. The laws of physics are not eternal. They are not written into the fabric of the universe from the beginning. They evolve. They change. The speed of light, the charge of an electron, the gravitational constant, all of it is temporary. The laws you learned in school describe the universe as it is right now, in this phase, in this era. But they were different before, and they will be different again. What survives across all those changes is time itself. Time is the container. Everything else is the contents, and the contents shift. Now think about what that means. If Ravelli is right and time is an illusion, then the laws of physics are permanent. They sit there in the timeless equations, fixed, eternal, beautiful. You lose time, but you gain stability. If Smolin is right and time is real, then the laws of physics are not permanent. The speed of light could change, the strength of gravity could drift, the rules that hold atoms together could weaken or tighten or vanish entirely. You gain time, but you lose the ground under every equation ever written. Two of the most respected physicists on the planet. Two positions that cannot both be true. And both of them destroy something you need. Pick Ravelli. Time disappears. You do not move through the world. You are frozen in a web of relations that your brain mistakes for a river. Pick Barber. Time and motion both disappear. You are a pattern inside a still photograph that contains the illusion of a projector. Pick Smolin. Time survives, but the laws of physics become temporary. The constants are not constant. The rules are not rules. The foundation shifts under your feet while you are standing on it. There is no option that leaves the world intact. There is no door in this hallway that opens onto solid ground. Every door opens onto a different kind of fall. But so far, this has all been theory. Equations on paper. Books on shelves. Arguments between brilliant people in rooms with blackboards. You could walk away from all of it and say, these are just models. The real universe is out there, made of rocks and stars and light, and in the real universe, time works the way it always has. Except, there are places in the real universe where time stops working. In 1916, barely a year after Einstein published his general theory of relativity, a German physicist named Carl Schwarzschild solved Einstein's equations for a perfectly spherical mass. He was doing it from the trenches of World War I. He mailed the solution to Einstein from the Russian front. The solution describes something that should not exist. If you compress enough mass into a small enough space, the geometry of space-time curves so steeply that nothing can escape. Not matter, not light, not information. The boundary where escape becomes impossible is called the event horizon. Here is what happens to time at that boundary. Imagine someone falling toward a black hole. You're watching from a safe distance. You see them approaching the horizon. As they get closer, their clock slows down. Their movements become sluggish. The light coming from their body shifts to red, then to deep red, then to infrared, then to nothing. They get dimmer, slower, and they never cross the line. From your perspective, they hang there at the edge of the horizon forever. Their clock approaches zero and never reaches it. They are frozen at the boundary for eternity. Now switch to their perspective. They feel nothing at the horizon. No barrier, no wall, no sign that anything changed. They cross it instantly and continue falling. Their clock ticks normally. Their heart beats normally. They do not notice the boundary at all. Two observers. One sees a person frozen at the edge of time forever. The other feels nothing and falls straight through. Both are correct. Neither is seeing an illusion. The universe does not pick one version. It runs both. Time is not slowing down at the horizon. Time is splitting into two realities that will never agree with each other again. What waits on the other side of the horizon is worse. Inside a black hole, the mathematics of general relativity does something that sounds like a glitch, but is not. The coordinates for space and time switch roles. Outside the horizon, you can move freely in space. Left, right, up, down. You choose your direction. But you cannot move freely in time. You move forward. Always forward. That is the one direction you cannot reverse. Inside the horizon, the arrangement flips. The radial direction, the direction toward the center, becomes time-like, and the time direction becomes space-like. What that means is that falling toward the center is no longer a movement through space. It is a movement through time, and just as you cannot stop moving forward in time outside the horizon, you cannot stop falling toward the center inside the horizon. You are not being pulled. There is no force dragging you. You are moving through time, and the center is where time goes. In 1965, Roger Penrose proved that this has an endpoint. His Singularity theorem, the work that won him the Nobel Prize in 2020, demonstrated that under certain conditions, gravitational collapse inevitably leads to a singularity, a point where the curvature of space-time becomes infinite, where density becomes infinite, where every known law of physics produces an answer of infinity, which in mathematics is another way of saying the equation has broken. The law no longer applies, the description has failed, the sentence has ended. At the singularity, time does not slow down, time does not stop. Time ceases to be a meaningful concept. There is no after the singularity. There is no next moment. The word next requires time, and time is what just ended. You are not falling toward a place, you are falling toward the edge of the last moment, the last tick, the point where the clock does not stop but ceases to exist. And you reach it not because something pulls you there, but because the structure of space-time inside the horizon gives you no other direction to go. Time inside a black hole has a wall, and you are always walking toward it. In 1974, a young physicist named Stephen Hawking discovered something about black holes that no one expected. They are not permanent. They evaporate. Hawking showed that the event horizon is not a clean boundary. At the quantum level, Pairs of particles are constantly appearing and disappearing everywhere in the universe. This is normal. It happens in empty space all the time. A particle and its antiparticle pop into existence, exist for a fraction of a second, and annihilate each other. Nothing gained, nothing lost. But at the edge of a black hole, something different happens. A pair appears right at the horizon. One particle falls in, the other escapes. The escaped particle carries energy away from the black hole. The black hole loses a tiny amount of mass. Over time, an unimaginably long time, the black hole shrinks, and eventually it disappears. Completely. Hawking radiation. A black hole the mass of the sun would take 10 to the power of 67 years to evaporate. That is longer than the current age of the universe by a factor that has no name in everyday language. But it happens. Given enough time, every black hole in the universe will be gone. Now here is the problem. Information fell into that black hole. Stars fell in. Planets fell in. Light fell in. Every object that crossed the horizon carried information about its structure, its composition, its history. That information went past the horizon and toward the singularity where time ends. And then the black hole evaporated and left nothing behind but a faint glow of thermal radiation. Where did the information go? If it was destroyed, then a fundamental principle of quantum mechanics is broken. Unitarity. The rule that says information is never lost. Every process in quantum mechanics is reversible in principle. You can always reconstruct the input from the output. If the black hole erased the information, that rule fails. The foundation of quantum theory cracks. If the information was not destroyed, then it had to get out somehow. But the event horizon is a one-way boundary. Nothing escapes. That is the definition of a black hole. So how does information get out of a place that nothing can leave? Hawking spent 30 years arguing that the information was gone, destroyed. He said quantum mechanics would have to bend. In 2004, he publicly reversed his position. He conceded that information survives, but he did not explain how. No one has. The information paradox has been open for 50 years. 50 years of the best minds in physics working on one question. Time ends inside the black hole. The object that contained the time evaporates. But the information that fell into that time does not disappear. Time dies. Its contents do not. The thing and what the thing contained are not the same. And no one can explain how that is possible. You could tell yourself that none of this matters. Black holes are exotic objects, theoretical monsters at the far edges of the universe. You will never fall into one. You will never see one. They are problems for physicists, not for you. But in April 2022, the Event Horizon Telescope collaboration released an image, not a simulation, not an artist's impression, a photograph. Sagittarius A star, the black hole at the center of the Milky Way, 4 million times the mass of the sun, 26,000 light years from where you are sitting. It is not at the far edge of the universe. It is at the center of your galaxy. Every star you have ever seen in the night sky is orbiting it. The sun is orbiting it. The Earth is orbiting it. You are orbiting it, right now, at this moment, at a speed of 230 kilometers per second, completing one lap every 225 million years. The last time the solar system was at this point in its orbit, dinosaurs had not yet appeared. The time before that, the most complex life on Earth was a fish. And at the center of that orbit, inside the object that everything you know is circling, time equals 0. The same equations that correct the clock in your GPS, the same general relativity that adjusts the timestamp on your phone every second of every day. Those equations say that at the center of Sagittarius, A star, time ends. Not in a thought experiment, not in a philosopher's argument, in the same mathematics that guides your car to the airport. You are gravitationally bound to an object where time does not exist. You have been circling it your entire life. Every person who has ever lived has been circling it. The distance feels safe. 26,000 light years. but distance is just space, and you are connected to that object not through space, but through gravity. The same gravity that bends your time by 38 microseconds a day on a satellite is the same gravity that bends time to zero at the center of the thing you orbit. The difference is not in kind, it is in degree. You are not far from the end of time. You are on a leash attached to it. Time breaks at the singularity of a black hole, but a black hole is a point, a local failure, a crack in the floor of one specific room. The question that follows is whether the entire floor is cracking, whether time has a limit not just in one place, but everywhere. In 1852, a physicist named William Thomson, later known as Lord Kelvin, followed the second law of thermodynamics to its conclusion. Entropy increases, disorder grows, gradients flatten, hot things cool down, cold things warm up, differences disappear. This is the arrow, this is the direction, but the arrow has a destination. If entropy always increases, then eventually it reaches a maximum. There is nothing left to spread. No temperature difference to equalize, no gradient to flatten, no energy available to do work. The universe reaches thermodynamic equilibrium. Every point in space is the same temperature. Every particle has the same energy. Nothing flows, nothing changes, nothing happens. Kelvin called this the heat death of the universe. It is not dramatic. It is not a collapse or an explosion. It is the opposite. It is the moment when the universe becomes so perfectly uniform that the word moment stops having content. Think about what that means for time. If time is the measure of change, as Aristotle said, and if Boltzmann was right that the direction of time is the direction of increasing entropy, then what happens when entropy has nowhere left to increase? There is no more change to measure. There is no more direction to point in. The arrow has arrived at its target and there is nothing on the other side. Time does not stop in the heat death. That would imply something is still there to be stopped. Time empties out. The word passes loses its meaning because there is nothing left to pass. The container remains, but the contents are gone. You are left with a universe that exists, but in which nothing, including time, has anything left to do. In 1998, two teams of astronomers pointed their telescopes at distant supernovae and discovered something that should not have been possible. The universe is not just expanding, it is accelerating. Saul Perlmutter led one team, Brian Schmidt and Adam Rees led the other. They shared the Nobel Prize in 2011 for a discovery that changed the shape of the future. The expansion of the universe is speeding up. Something is pushing galaxies apart faster and faster. Physicists call it dark energy, which is a polite way of saying we do not know what it is, but we can see what it does. And what it does is separate everything from everything else. Right now, the observable universe contains roughly 2 trillion galaxies. You can point a telescope at them, you can photograph them, you can measure the light they emit and calculate their distance and their speed. But they are moving away, and they are moving away faster every year. In roughly 100 billion years, every galaxy outside the local group, the small cluster that includes the Milky Way and Andromeda, and a few dozen smaller galaxies, every galaxy beyond that cluster will cross the cosmological horizon. Their recession speed will exceed the speed of light. Not because they are moving through space faster than light, because the space between us and them is stretching faster than light can cross it. Once they pass the horizon, their light will never reach us again. Not eventually. Not with a better telescope. Never. The photons they emit will run toward us forever and never arrive. Those galaxies will not explode. They will not collapse. They will simply become invisible. Permanently. Irreversibly. The sky will go dark. Not all at once. Slowly. Star by star. Galaxy by galaxy. 100 billion years from now, an astronomer standing on whatever is left of Earth will look up and see the Milky Way and nothing else. A single galaxy in an infinite void. And there will be no evidence that anything else was ever there. The light is gone, the records are gone, The universe will look like a single island in an ocean of nothing, and no measurement and no instrument and no theory will be able to prove that the ocean once had other islands. The universe will not end with a collapse, it will end with forgetting. Everything that existed beyond your reach will be erased from the record as if it never happened. And time will still pass, but there will be nothing left for it to carry. But the block universe says something worse. If Minkowski was right, if the four-dimensional structure is real, then the heat death is not waiting in the future. It is not an event that will happen in 100 trillion years. It is a region in the same structure that contains the moment you're experiencing right now. Think of a road. You are standing in the middle. To the east, the road stretches to a city. To the west, it stretches to a desert. The city and the desert both exist right now. The city does not stop existing because you are not standing in it. The desert does not start existing when you drive toward it. They are both already there. The block universe says the same thing about time. The Big Bang is a region. Your life is a region. The heat death is a region. They are all parts of the same four-dimensional object. None of them is more real than any other. None of them is waiting. The death of the universe is not something that will eventually happen to you. It is something that is already there, in the block, at the same level of reality as this sentence. You are not traveling toward it. You are next to it. The feeling that it is far away is a property of your position inside the block. From outside the block, there is no distance between now and the end. There is no between at all. The beginning and the end are neighboring regions of a single object, like the first page and the last page of a book that is already printed. You are not reading toward the last page. The last page is already written. It is already bound. It exists right now with the same certainty as the page you are on. You do not live before the end of time. You live next to it. In 2010, Roger Penrose proposed that the end might not be the end. Not because something comes after it, but because the end and the beginning are the same thing. The theory is called conformal cyclic cosmology. CCC. Here is the logic. In the far future, the universe reaches heat death. All matter has decayed. All black holes have evaporated. The only things left are massless particles, photons, and a photon has a peculiar property. It does not experience time. This is not a metaphor. In special relativity, a particle moving at the speed of light has a proper time of 0. Its internal clock does not tick. It does not age. It does not experience duration. For a photon, the moment of emission and the moment of absorption are the same moment. A universe made entirely of photons is a universe in which no particle has a clock. And if no particle has a clock, the universe loses the ability to measure scale. Distance becomes meaningless. Size becomes meaningless. The difference between very large and very small disappears. Penrose realized that in this state, an infinitely expanded cold universe is mathematically identical to an infinitely compressed hot point. The numbers are the same. The geometry is the same. The description is the same. The heat death of one era is the Big Bang of the next. Not metaphorically, conformally. The transition does not require energy. It does not require a mechanism. It does not require time, because time is exactly the thing that has lost its meaning. One era fades out. The next era emerges. And there is no boundary between them because a boundary would require a scale, and scale is what just disappeared. Penrose looked for evidence. He predicted that gravitational waves from the previous era, from collisions between supermassive black holes in the universe that existed before ours, would leave imprints in the cosmic microwave background. Concentric rings, faint temperature anomalies in the oldest light we can detect. He searched the data from WMAP and Planck. The results are disputed. Some teams found the rings, others did not. The debate continues, but the model stands. Time does not end. It does not begin. It loses itself and starts over with no memory of what came before. You cannot know which cycle this is, and the word which assumes a sequence, and in this model, there is no sequence. There is no first cycle and second cycle. There is only a structure that has forgotten itself so completely that forgetting and beginning are the same act. Theories can argue, data cannot. In the last 3 decades, laboratories have started returning results that do not fit neatly into any of these models. Results that attack the most basic assumption your brain makes about reality. That causes come before effects. In 2007, a team led by Vincent Jacques at the École Normale Supérieure in Paris ran an experiment that John Wheeler had imagined in 1978. A single photon enters an apparatus. A beam splitter gives it 2 possible paths. At the end of the paths, a decision is made by a random number generator. Insert a second beam splitter, or do not. If the second splitter is there, the photon displays interference, wave behavior, both paths at once. If the splitter is not there, the photon hits one detector, particle behavior, one path. The critical detail is the timing. The random number generator makes its decision after the photon has already entered the apparatus, after it has already passed the first beam splitter, after it has already, by any normal understanding of the word, committed to its path. But the results show that the photon's behavior at the first beam splitter depends on what happens at the second. A decision made in the future determines a fact in the past, not a reinterpretation of the past, not a fuzzy maybe. The interference pattern either exists or it does not, and its existence is controlled by a choice that has not been made at the time the pattern is being created. The experiment has been reproduced dozens of times. No model based on hidden variables has survived the data. No explanation that preserves the normal order of cause and effect has held up. The photon does not guess, it does not hedge. The past is not settled until the future acts on it. And the machine that proved this is not a billion-dollar collider. It fits on a table. In 1999, 2 physicists at the University of Maryland, Yoon-Ho Kim and Yanhua Shi, built a variation that goes further. The delayed choice quantum eraser. The setup starts with a pair of entangled photons. One is called the signal photon, the other is called the idler. The signal photon passes through a double slit and hits a detector screen. Normally, a photon going through 2 slits produces an interference pattern, bright bands and dark bands, wave behavior. But if you can determine which slit the photon went through, the interference vanishes. Particle behavior, one path. In this experiment, the idler photon carries the information about which path the signal photon took. The signal photon hits the screen and is recorded. The data is saved. The pattern on the screen is fixed. Then, later, a choice is made about the idler. If the which path information is erased, the interference pattern appears in the signal photon's data. If the which path information is preserved, the pattern disappears. The signal photon has already been detected. The data has already been written down. Nothing changes on the screen after the fact. But when you sort the signal photon's data according to what happened to the idler later, the pattern is either there or it is not. The past did not change. Something stranger happened. The past contained both outcomes at the same time. The interference pattern and the absence of the interference pattern were both embedded in the data from the beginning. And the future decided which one was real. The past is not a single fixed record. It is a superposition of records. And the future is the thing that collapses the superposition into one version. Causality is not a line pointing from yesterday to tomorrow. It is a web where tomorrow reaches back into yesterday and selects which yesterday actually happened. Both of those experiments break the order between 2 events. A happens before B, but B determines A. That is strange enough. But in 2017, a team led by Giulia Rubino at the University of Vienna did something that removes the order entirely. The experiment is called a quantum switch. The setup involves 2 quantum operations, A and B. In classical physics, either A happens before B or B happens before A, one or the other. There is always an order. Even if you do not know the order, it exists. Rubino's team placed the control system in a quantum superposition. The result is that operation A happens before B and after B at the same time, not one or the other, both, simultaneously. The causal order itself is in superposition. This is not an interpretation. The experiment produces a measurable result. When the causal order is in superposition, the system achieves a computational advantage that is impossible under any fixed ordering of A and B. You cannot get the same result by running A first and then B. You cannot get it by running B first and then A. You cannot get it by flipping a coin and choosing randomly. The advantage only exists when the order itself is undefined. The experiment has been reproduced in multiple laboratories. The results are consistent. The causal order between two events is not a fact about the universe. It is a quantum variable. It can be put into superposition the same way a photon's position can. Before and after are not fixed properties of reality. They are observables. Their values depend on how you measure them. At the deepest level of physics, the sentence A happened before B does not have a definite truth value until someone performs a measurement that forces it to pick one. 10 spirals down. Time has no definition. Its direction is a statistical accident. The present moment is personal. Your brain fabricates the flow. Quantum mechanics breaks causality. The best equations erase the time variable. Black holes end time physically. The universe is heading toward a state where time empties out. Experiments show that the future determines the past, and the causal order is a quantum variable. All of that points in one direction. Time is not fundamental. But there is one experiment that points the other way. Just barely. In 2019, the LHCb detector at the Large Hadron Collider at CERN observed a process in which the symmetry between forward and backward in time is broken. The decay of d mesons, particles made of a charm quark and an up antiquark. When these particles decay, the process does not look the same when you reverse time. The CPT theorem, the same theorem from the 1950s that told us all fundamental laws are symmetric, says that a violation of CP symmetry is equivalent to a violation of T symmetry, time reversal symmetry. The LHCb results show a genuine asymmetry. Time has a preferred direction at the level of fundamental law, but the size of the asymmetry is what matters. It appears in one type of decay of one type of particle, and the magnitude is a fraction of a percent. Everything else in physics, every other process, every other particle, every other interaction, is perfectly reversible. The arrow of time you feel every day, the one that makes coffee cool and memories form and cells age, has no connection to this tiny crack in the symmetry of d meson decays. The only place in all of fundamental physics where time has a direction is in a fraction of a percent of one process, and the entire rest of the universe is silent on the question. The arrow you live inside has no explanation at the level of law. It has an explanation at the level of statistics, and the statistics rest on an assumption that no one can justify. We are back where Boltzmann stood, except now we know how deep the hole goes. There is a reason no one has answered the question. The two theories that describe the universe with the highest precision ever achieved disagree about what time is. General relativity says time is dynamic. It bends. It stretches. It slows near massive objects. It is part of the fabric of space-time, and that fabric is shaped by the matter and energy it contains. Time is not a background. Time is a player. Quantum mechanics says the opposite. In quantum mechanics, time is a fixed parameter. It sits outside the system. It does not bend. It does not respond to matter. It ticks at a constant rate, providing a stage on which quantum events unfold. Both theories are confirmed to extraordinary precision. General relativity predicts the orbit of Mercury, the bending of light around galaxies, the expansion rate of the universe. Quantum mechanics predicts the spectrum of hydrogen, the behavior of semiconductors, the existence of the Higgs boson, 14 decimal places of accuracy. They are the two most successful theories in the history of science. And they cannot both be right about time. Time cannot be both dynamic and fixed. It cannot be both part of the fabric and external to the fabric. It cannot bend and also not bend. To unify these two theories, to write the one equation that contains both, you have to decide what time is. That is the problem of quantum gravity. It has been open for 90 years. String theory tried. It produced a landscape of 10 to the 500 possible solutions, and no way to choose between them. Loop, quantum gravity tried. It removed time and replaced it with a network of discrete quantum states, and could not recover the smooth space-time of general relativity at large scales. Causal dynamical triangulation tried. Causal set theory tried. 90 years. 4 generations of physicists. In that time, science split the atom, landed on the moon, sequenced the human genome, detected gravitational waves, and photographed a black hole. And in those same 90 years, it made zero progress on the question of what time is. Not slow progress, not incremental progress. Zero. The people who have spent their lives closest to the answer do not agree on what they found. 3 voices, 3 positions, none compatible with the others. Carlo Rovelli, loop quantum gravity, the order of time. His position is that the world is not made of things that persist through time. It is made of events, happenings, processes that have no duration, only relations to other processes. Time is not a river carrying events along. Time is the name we give to the fog that prevents us from seeing all the relations at once. Clear the fog and time vanishes. What remains is a web. Static, complete, timeless. Julian Barber, the end of time. His position is more radical. Not only does time not exist, motion does not exist. Change does not exist. There are only configurations, frozen snapshots, each one a complete universe, none connected to any other by sequence or causation. Your experience of flow is a feature of the configuration you inhabit, like a picture of a river painted on a canvas that has never moved. Lee Smolin, Time Reborn. His position is the opposite of both. Time is the only thing that is real. Space is derived from it. Laws are derived from it. Constants are derived from it. And all of them change. The speed of light is not permanent. The gravitational constant is not permanent. The equations that describe reality today are not the equations that described it a billion years ago. 3 physicists at the top of the field. 3 answers to the same question. Rovelli says the world is a web and time is fog. Barber says the world is a photograph and time is a painted river. Smolin says the world is a process and time is the only real thing in it. Choose Rovelli and you lose time. Choose Barber and you lose time and motion and change. Choose Smolin and you lose the stability of every physical law. There is no position in this debate that does not cost you something fundamental. There is no answer that leaves your picture of reality intact. These are their published positions, their books, their lectures, their equations. But there is a difference between what a person writes for the public and what they say when someone asks them how it feels. Sean Carroll, Caltech, one of the most cited cosmologists in the world, host of the Mindscape podcast, author of books that have translated quantum mechanics and general relativity and entropy into language that millions of people can follow. In 2023, in a conversation about the nature of time, he said this: "We do not know whether time is fundamental, and I am not confident we will know in the coming decades. That is not a fringe physicist hedging his bets. That is one of the most prominent scientists alive saying, plainly, that the question is stuck." Carlo Rovelli. In an interview in 2018, speaking not as a theorist, but as a person, said this: "When I think about the possibility that time does not exist, I feel a vertigo. A physical vertigo. The man who wrote the equation that removes time from quantum gravity feels dizzy when he considers that his equation might be right. Lee Smolin. In Time Reborn, not in the technical chapters, but in the passages where he stops calculating and starts reflecting, wrote this: "The question of the nature of time is the question on which everything else depends. Whether we can understand the universe at all depends on whether we can understand time. And we do not understand it. 3 people who have gone further than anyone else. 3 people who have spent decades at the edge, and when you ask them not what they think, but what they feel, the answer is the same. Vertigo, uncertainty, silence. They are not hiding the answer. They are not protecting it. They are not waiting for the right moment to reveal it. They are standing at the edge of a cliff, and they cannot see the bottom. The title of this video is Something About Time. Terrifies scientists, and they will not explain why. Now you know why. It is not because they will not. It is because there may be nothing to explain. The thing they found at the bottom is not an answer. It is an absence where an answer should be. An absence is harder to explain than any fact. Everything you heard tonight is true. Time has no definition. The greatest minds in 3,000 years of human thought could not write one. Its direction is not a law. It is a consequence of a starting condition that no one can explain, held up by a probability so small the number does not fit in the universe it describes. The present moment does not exist in the structure of reality. It depends on your speed and your altitude, and it belongs to you and to no one else. Your brain does not observe time. It manufactures it. It fakes the order. It fakes the duration. It fakes the link between cause and effect. It pastes it all together and presents it to you as a seamless flow, and the flow is a construction, and the seams are hidden, and the thread is not real. At the quantum level, the deepest flaw of reality, the future determines the past, and the causal order is a variable that can be put in superposition. The best equations in physics describe the universe without the letter T. Black holes end time at a point you orbit every 225 million years. The universe is heading toward a state where time loses all content. And the people who know this best, the ones who have spent their lives at the bottom of the question, are quiet. Not because they are hiding something, because they reached the place where the ground was supposed to be and found air. That is the truth, and it is allowed to frighten you. It should. A species that discovers it cannot define the most basic feature of its own existence, has earned the right to be unsettled. But here is the part they will not say, and I will. You are here. Right now. Whatever now means, whatever here means. Whatever the word you refers to in a block universe where every moment already exists, you are experiencing this. You are processing these words. Something in you is turning symbols into meaning. And that thing, whatever it is, does not require an equation. It does not require a definition. It does not need permission from physics to exist. The question of what time is may never be answered. The floor may never be found. The cliff may not have a bottom. But you are standing. You are breathing. You have things you want to do and places you want to go and people you want to become. None of that needs the question to be solved. None of that waits for physics to make up its mind. Do not spend the time you have being afraid of what time is. Live it. Chase the things you want. Build what matters to you. Remember who you are when no one is watching. Be kind to yourself on the days when the ground feels thin. I believe in you. Thank you for being here with me.